I was telling you that so with LES you can save some CPU, but still it is very demanding in terms of resources, computer resources, because you have to solve the big scales but also some of the small scales. So then the people have developed another technique which is called Reynolds average Navier-Stokes equation. So I'm presenting that after the LES, but actually it has been proposed way before. Okay, so because I'm showing the different techniques in a let's say pedagogical order, which is DNS you don't have any modeling, LES you are just modeling the small scales, Reynolds average and Navier-Stokes equation I'm going to explain. But in reality, the Reynolds average Navier-Stokes equation is existing for let's say between 30 and 40 years, compared to large eddy simulation, which is existing for at maximum 10 years. Okay, so it's quite recent, and it is recent because it's still time consuming. So this is why it has been developed when the computer power has been expanding. So this technique this approach of modeling is very popular, and this is the one that you can find in all the CFD softwares like Fluent, like CFX, like Saturn, all the commercial codes, OpenFOAM and COMSOL, and all these codes, all these software, they are using that technique because it is not very time consuming, and then you can use it to have a rough idea of the flow. So the idea of that modeling is to take advantage of the randomness of a turbulent flow. Okay, so let's say that you have a turbulent flow. So let's say you have the flow in a pipe, and in that flow in a pipe you have many vortices because the flow is turbulent. Okay, so the Reynolds number is much higher than the 2000. And now let's assume that you have a probe, a velocity probe somewhere. Okay, so you are able to measure the velocity intensity at some point. So this afternoon I will explain how you can do that with some experimental equipments. And then you measure the velocity as a function of time. Okay, so if the flow is laminar, it will be like that. Okay, in a Poiseuille flow, the flow is steady. So if you have a probe and you measure the velocity, it will be constant in time. So this is for laminar flow. If the flow is turbulent, then your measure will be like this. Okay, you have fluctuations because the probe is going to measure the velocity at that point, but at that point you have flow turbulence which is passing over, and you have small structures, big eddies, small eddies, and so on, and each of them is going to give you a certain velocity. Okay, so the flow, so this is when it is turbulent. Okay, this is when it is turbulent. So the main idea of Reynolds, the same Reynolds as the Reynolds number, is to take an average, because when you are an engineer, actually you don't care to be able to model all these structures. What you want to know is what will be the flow rate. Maybe you want to know what will be the range of variation. So if you have the average and the RMS, that's more than enough for designing your process. You know, you can design, you can select the pump to generate the flow rate. That's enough. Okay, so the idea is you don't need to have all this information about the flow structures. The information you would like to obtain is the mean. So you want to get the average. So I will call it V bar. This is the average. And maybe you want to evaluate the RMS value, V prime. Okay, that could be enough to get an idea of the intensity of turbulence. So this is the main idea which has been used in the Renners decomposition. So you say that the flow field, the velocity field, which may have three components, of course. Maybe you are measuring only one component, but you have three components. It is depending on time, on space, because if you place the probe here or here or here, you will not get exactly the same answer. It is depending on time, of course, as you see. It is fluctuating because of turbulence. And then the idea of the decomposition is to look for statistics. Okay, you are not going to look for the full fluid flow, but for statistics. So you are going to look for the mean, U bar, and U prime, which is the deviation from the mean, the fluctuation from the mean. And then the job is to evaluate, to calculate what are the equations for the evolution of the mean. Not the equation for the flow field, because we know that the equations are the Navier-Stokes equations. So the question is, if I take the Navier-Stokes equation, what would be the modifications of these equations to predict the mean, okay, instead of the instantaneous flow field. And then there's the work of averaging. Okay, there's some mathematical operation that you need to do to transform the Navier-Stokes equations into a new set of equations which are going to give you the evolution of the mean, but not of the flow field, of the mean only. And when you do that, unfortunately, there is a loss of information. So I'm going to explain you, that will be a bit time consuming to show you the equation. It's not complex, it's not very complex, but I need a big board. But I'm going to try to explain you what is the problem. So let's say that you have two variables. So you measure V and you measure U. Okay, so you measure two components of the flow field, U and V. Okay, and for both of them, you are going to use this decomposition, U bar plus U prime, V bar plus V prime. Okay. In the Navier-Stokes equations, you have many terms. Okay, so you have du by dt, you have u grad u, you have the Laplacian of u, so you have many terms. So let's say that you take du by dt. Okay, du by dt, you want to take the average. Okay, so it will be du bar plus u prime over dt, and you still have the bar here. Okay, so you use the decomposition, u as mean plus fluctuation, you take the average, so that will be d over dt u bar plus u prime, okay. Taking the average of the sum is the same as the average of the sum. Okay, the average of the sum is the sum of the two averages. Okay, if I have two students, you have 10, you have 20. The average of 10 and 20 is 15. Okay, so this is the average of 10 plus 10 plus 20. So okay, so when you have a summation, you can split the average. So it will be du over dt u bar plus u prime bar, and by definition u bar is the mean. The mean of the mean is the mean. Okay, when you take the mean here and you retake the mean, it's of course the same. So that will be d over dt over u bar, and of course u prime average is 0 by definition, because u prime is just what is missing from the instantaneous flow field to the mean. So when you make the average of the extra fluctuation, that will be of course 0. Okay, so you see that if you take one term of the Navier-Stokes equation, the average, the temporal evolution of the average is actually, so the average of the temporal evolution is the temporal evolution of the average. So you see that there is no problem here. This is the same formulation. So now if I take another term in the Navier-Stokes equation, if I take another term of the Navier-Stokes equation, like the divergence of u, so this is a product. So at some point I will have a product like uv, okay, like this. If I take the average of that, so that will be again u bar plus u prime v bar plus v prime bar, like this. Okay, so I can develop this, so that will be u bar v bar, u prime v bar, u bar v prime, u prime v prime, and still the average. Okay, I just expand this product. So I can cut the bar, so it's u bar v bar bar, okay, because this is the sum, the average of the sum is the sum of the averages. And now I'm going to use the fact that you have already average, so that will be u bar v bar plus u prime bar v bar bar plus u bar v prime bar bar plus u prime v prime bar. Okay? And here I'm using again that u prime bar is 0 and v prime bar is 0. Okay, so finally I end up with u bar v bar plus u prime v prime bar. Okay? So if we compare these two expressions, you see that for the temporal derivative, the average of the temporal derivative is actually the temporal derivative of the average. So you see that there is no modification in the equation. This is the same term. You just have to add a bar. So the Navier-Stokes equation for that term will not be modified. But and that will be the same actually for all the linear terms. Because when you take the average of a linear term, that will be the average, the same term but with a bar. Okay? But unfortunately, in the Navier-Stokes equation, you have a non-linear term. You have the product of something, the product of u by its gradient, you have the product of u by u. Okay? And when you have the product, you see that the average of the product is the product of the two averages plus an extra term. Okay? This term is generally non-zero. Do you know when it is 0? Yeah, exactly. So for this average u prime v prime bar to be 0, you must have two variables, u prime and v prime, stochastic variables, which are completely independent. So there's no correlation between that two. But of course in a fluid there is correlation, because when you have a vortex like this, in turbulence you have many vortices, so you cannot say that this component and that component are completely decorrelated, because that would mean that the fluid is moving in different directions without any correlation, and we know that it is not the case because you have these flow structures. It is complex, but still you have the vortices. So u prime and v prime, you may assume that these are stochastic variables because you see fluctuations like a random variable, but these two variables are correlated. There is some correlation. So in turbulence, this is for sure non-zero in turbulence. And the beauty of the Navier-Stokes equations is you see that these terms are related to turbulence, and they are coming from the nonlinear terms, which is the source of the turbulence. Because when you increase the Reynolds number, you increase inertia. When you increase inertia, you increase the weight of that term. So you see that everything is connected. The physics is connecting with the mathematical properties of the Navier-Stokes equation. The source of the turbulence is inertia. Inertia is nonlinear terms. When you increase the Reynolds number, you increase the weight of the inertia terms, and then you generate fluctuations, which is going to contain the effect of turbulence because it is non-zero. So this is the beauty of mathematics and physics and all these things. The problem is, you see that in the Navier-Stokes equations, in the Reynolds, so we call them Reynolds average Navier-Stokes equation, Renners modeling. In these new equations, all the linear terms will be exactly the same. So du by dt, gradient of p, Laplacian of u, gravity, of course, gravity is constant. So all these terms will be exactly the same, you just have to add a bar. But the nonlinear term will generate new objects, new terms in the equations. And the problem is that we don't know that. Okay, so we are, initially you start with equations which are closed. I mean, in the Navier-Stokes equation, you have 3 equations for the 3 component of the momentum balance, plus the divergence of u, so that is 4 equations. Okay, you have 4 equations. And you have u, v, w, p as unknown. So you have 4 equations, 4 unknown, so that should match. Maybe you don't know how to solve it, you don't know, but there is a solution, and the flow is actually the solution. You can see the flow, but this is the solution. So you can match the two, and indeed you can find the solution. But then, when you look at the Reynolds average Navier-Stokes equation, you still have 4 equations. Divergence of u bar, and the 3 components of the Reynolds average Navier-Stokes equation. So you still have 4 equations. But the unknowns are u bar, v bar, w bar, p bar, plus u prime v prime bar, u prime bar, u prime w prime bar, v prime bar, v prime w prime bar, w prime bar, w prime bar. So you have extra unknowns in your system. And you end up with 4 equations, 10 unknowns. And you are stuck. Okay? You don't know what to do. Because even if you take the computer, the most powerful you find, you take the best mathematician you can find, he cannot solve a system of 4 equations with 10 unknowns. It's impossible. Okay? So there is a need of modeling. I mean, you need to evaluate all these new extra terms as a function of u bar, v bar, w bar, and p bar. So you have to make a connection between the new unknowns and your 4 variables, your 4 primitive variables. Okay? And the way you do that is by modeling. Modeling means you are going to write something, to write maybe an equation, to write something. And when you write that, of course, you make mistake because you don't know. You don't know how this is going to be related to that. So you are going to propose something, and there are different models. Some of them are very simple, some of them are very complex, but all of them are models. And then when you use a model, you have errors. Because the model will be always related to some theory. You are going to assume that, I don't know, something, u prime v prime bar is evolving like the gradient of u bar, for example. Well, why not? But that will be based on assumptions. And these assumptions, when you have a complex flow in the industry, might be valid somewhere in the flow, but might not be valid at another place. Okay? Or it might be valid for this Reynolds number, but not for the other Reynolds number. Or it might be valid for that geometry, but if you change the geometry, the flow structure will be different, the model is not valid. And then if you look in a software of CFD, you have plenty of models. So I can give you some names. So you have K epsilon, you have IG epsilon, you have mixing length, you have K omega, low Reynolds number models. So you have maybe 10, and you can find in research papers, I don't know, hundreds of models. And each of them have advantages and disadvantages. They can be used in that configuration, but not in that configuration, for that Reynolds number, but not for that Reynolds number. And then if you don't know that, and you take the CFD software, and you say, okay, I'm going to do a simulation in a pipe with a bend, and then there's a convergent and a divergent, and then something, and there's a blade, and I don't know. And then you have this list of models, and then you say, okay, what should I choose? So if you don't have any background in fluid mechanics, okay, you are going to click, and then the code is going to solve the equation, and then you will get a picture with a flow. But is it meaningful? Okay, and this is all the difficulty, and this is why we are training students in fluid mechanics. It's because at some point in their job they will use CFD, because it is very useful to understand things and to do design and optimize. But if you do simulation but you don't have any background in fluid mechanics, you are going to do wrong simulations, just because there is modeling issues. There are modeling issues in the CFD. If you do direct numerical simulation, there is much less problems, because you solve exactly the Navier-Stokes equations without any modeling. So you cannot make too much mistake. You can make mistakes in writing the codes, of course, but you can check in selecting the algorithm. So you can make mistakes, but actually it's not your job. Your job is not to develop codes. You are not in applied mathematics. The guy in applied mathematics, they are trained to select that algorithm for that type of equation, that algorithm for that type of nonlinear term. So they are trained for that, and they can make a good job on that. So if you do that, you will make very much less errors. But unfortunately, as I told you, you cannot use this method for industrial scales applications and simulations. So you have to go to that, but for now it's not available in companies. So you have to go for sure for the runs modeling. And for the runs modeling, I tell you, there is tens of models, maybe hundreds of models. Some of them are implemented in Fluent, in softwares. Some of them are not, because the range of validity or the improvement was not very interesting, so they didn't decide to use them. Some of them are very complex, and because it is complex, they decided not to include that in the software, because you have also to keep in mind that as you are going to run a simulation, it has to be developed by someone. Okay, so if you say, okay, this model is very, very accurate, very good, but it is not available in your software, it means you are going to code it. And coding a model that could take you maybe 2 or 3 months. And if your boss is telling you, okay, I want the answer next week, okay, it's impossible. So you are very often the choices that you are going to do are completely biased, okay, because the model is not available, and also the time consuming. Some of the models are very precise, but they are very demanding in terms of CPU. So you are going to say, okay, this one is very good, but I'm not going to wait for 2 months. So I'm going to click on that one, and I will have the answer in 1 day. Okay. So you see that many of the choices that you are going to do are completely biased by non-scientific analysis. Okay. So be careful when you do CFD. If you don't have any background in fluid mechanics, there are 99% chance that you will be doing trash. Okay. Colors, but wrong simulations. Okay, so I can show you some videos so you can see maybe more clearly what are the different techniques: DNS, LES, and run simulations. So usually when I click here, it doesn't work. Yes, okay. So I have to go back. Okay, so I'm going to show you some videos just to visualize what are the different techniques of simulations. Okay, so on this video, what you see, so this is the flow. So the flow is coming from the left. So maybe it's better to look on the TV screen. So the flow is coming from the left, and then you have a cylinder here, a cylinder, and we look at the wake behind the cylinder. So when the Reynolds number is very low, you remember that the streamlines are touching the surface of the cylinder, and as you increase the Reynolds number, there is a wake, and the length of the wake is increasing with the Reynolds number, and at some point you have vortex shading. Okay, so this is what we see here. So you see in green the vortices which are rotating, so this is counterclockwise, and in red clockwise. Okay, and then it's a 3D simulation which is time dependent. Okay, it's completely unsteady. Okay, so you see the big vortices, but you see also the small vortices which are generating on the side of the vortex. So this is typical simulation with direct numerical simulation. Okay, so you solve only the Navier-Stokes equation, you increase the Reynolds number, and then you see the vortex shading, and you see the turbulence which is appearing. So same type of simulation, but now it's the flow around a cube. So you see the flow structure, which is very complex. So you see the big vortices, the small vortices, and again, this is direct numerical simulation. Okay, so you see that you have a lot of information because you can have, for example, the time scales of the detachment of the vortex shading. You can have the size. You have all the information because it is based on the full Navier-Stokes equations. Okay? Another one, same technique. Oh, that. So same technique. So now it's the flow driven by a moving wall. So at the top you have a wall which is sliding, and then it is entraining the flow by viscosity, by viscous friction, and it generates a big vortex, and inside that big vortex, so you see in the corners, you have many small vortices. So again, this is pure DNS at some Reynolds number. The problem is, if you increase the Reynolds number, you will decrease the size of all the small eddies that you see, and you need more and more and more refined mesh. Okay, so I don't know which one I have to show. Okay, so now the flow that we see is the flow over an obstacle. So the flow is coming from the left to the right, and here you will see, so it's a bluff body. Here you will see the wake and the turbulence which is generated in the downstream direction of the wake. Okay, so this is one type of simulation, but I have one where we see everything together. Okay, so this is the one. Okay, so you see on this panel, so four types of simulations. Okay, so this is the same flow, same domain, same configuration, same Reynolds number. Here we will look at DNS, direct numerical simulation, so with a very fine grid. Here we will look at LES with a model of a subgrid model, but the mesh is quite fine. And then here with a coarse, so and then the Reynolds average Navier-Stokes equation. So when you go from here to here, you coarsen the mesh. Okay, you have less grid cells, and the time the CPU demand is of course decreasing a lot by a factor. Let's say from here to here, it's probably by a factor 3 or 4. From here to here, it's probably by a factor of 10, and from here to here, it's probably by a factor of 100. Okay, and this is exactly the same flow, same boundary conditions, same Reynolds number, same geometry. The only thing which is modified is the refinement of the mesh and the model which are used. Okay, so we can compare. Okay, so first observation. So we still all of them are able to give you, let's say, you see the wake here. So here you have a recirculation zone, a region where you have a big vortex. So all the three simulations give you this information. So you see the wake here, you see the wake here, you see the wake, you see the wake. Okay. When you do DNS, what you get is all the small eddies into the wake. So all the turbulent eddies into the wake. When you do LES, you see that still you keep some of them because you are simulating the big structures. You have coarsened the grid, but still you refine some eddies. Then again, you coarsen, you lose some of them, but still you have some of them. If you look at the Reynolds average and Navier-Stokes equation, then you see what you miss. Okay, so you go from that, which is very close to the reality, it's very close to an experiment if you are at the correct Reynolds number. And if you go from there to there, you see all what you miss. So you see here, you don't have anything compared to the real solution or the accurate solution where you have a lot of turbulence. Okay? And then you wait. And when the steady state is reached, you see that at the steady state, of course, there is no steady state in terms of DNS because the flow is always turbulent, is always evolving in time, but it will be statistically steady. In the LES, you still have information. Here, you start losing information, and then in the Reynolds average Navier-Stokes equation, so you see what you get. You get the shape of the wake. You know that here you have an increase of viscosity, but here there's no more. There's nothing. No turbulence, nothing, compared to the reality where you still have a lot of information. Okay, so you see, when you go from pure Navier-Stokes equations to Reynolds average Navier-Stokes equation, you have to be aware that you are losing information. And it's not because the model is not correct. Probably that model would be the best that you can use for that. It's just based on this, that you are losing information when you solve the equations for the mean instead of solving the equation for the instantaneous flow field. But again, you cannot use that technique for industrial applications. It is very far from being possible, even during the next 10 years or 20 years. Okay? So you need to use that. But you have to keep in mind that the information you will get from CFD, you have to analyze that critically. You know that you are losing things, so you need to be trained to analyze what you get in the Reynolds average Navier-Stokes equation and how you can use this information to understand the physics of your process, to optimize your process, to make a better design and so on. Okay, but you have to keep in mind that you don't have the full information. Okay, you don't have the full information, and you may have also very different answers if you select another model which is maybe wrong in that situation. Okay? Okay, so this is the end for that part on introduction to CFD. Do you have any questions or comments? So of course that's not too much details because I don't have time to explain you how to write the equations, how to do the numerical modeling, the numerical techniques, how to use the software, but just want to warn you about using CFD. It is very useful, it is very powerful, but you need to be trained to understand what you get and to select the appropriate models.
Can I ask one question on behalf of them? Because
yeah, sure.
I was not here. But suppose when we are dealing with in-memory processing, we are dealing with slurry.
Mm-hmm.
So what are the basic assumptions I have to make while using the CFD to have my slurry to behave like it?
So for now I didn't address that because the introduction to CFD was only for single phase flow. Okay. So I'm going to come now to the two-phase flow. And then you will see that even for single phase, you see all the problems, all the difficulties, all the choices that you have to do. So to answer your question, I will show the different strategies that you can have for two-phase flow. And then you see you have many options in single phase. And then in two-phase, that will be that big. Okay, so you have much more methods, much more models, much more, because the phenomena are much more complex. So I'm going to give you some information about that.
And then another question for single phase, do I need to validate everything, whatever we are predicting?
Yeah, of course. When you get this, so let's say when you get this answer at the end, you may be questionable about that. So you need to.
Many times say actually here the validation means whatever the turbulence model I have used.
Mm-hmm.
So should I validate that also, that whether it is how do you normally validate that whether my selection of turbulence model, so it is only based on the response what you get?
No, basically what the different there's different way to answer. The first way would be if I am able to do a better simulation, but it is too time consuming, I'm going to validate the model for one operating condition over the best model I can use. So let's say DNS or IDS with my choice of modeling. And because I want to use this simulation extensively to look at the evolution, I don't know, with velocity, with you change something. So you are going to validate one model against another CFD model, which is much more time consuming, but much more accurate for one operating condition. And then if you are happy, then you are going to use that model for the other operating condition. So this is one way of validation. Another way of validation is to use your CFD code, and then you have some benchmark. So you have some experimental data, and then you are going to validate your model, your simulation against some data. But then you are facing problems because the simulation you are doing, you are not going to simulate maybe the whole thing. You are going to assume that the inlet condition is something, maybe in the reality it's not the same. You are going to assume that you know the physical properties. For example, you know that the viscosity is 1 point something, but actually it's not. So you are facing all the problems when you want to compare experiments with theory or with CFD. And then you might have errors coming from CFD, but you might have errors coming also for experimental data. So you have to be critical when you do that. You have to understand what are the errors coming from your choices in the CFD modeling, the CFD boundary conditions. Many problems are coming from the boundary condition. For example, here you have a boundary conditions because you have to stop your domain at some point. But in the reality, this flow is continuing in an experiment. So here you are applying numerical boundary conditions, which should generate no perturbation, like if the flow is evolving. But actually you are not solving the Navier-Stokes equation here, so you don't know what is the feedback effect of that boundary condition on the flow, and very often you have a feedback effect. So you have many questions about boundary conditions, about modeling. So you have to face these problems of CFD validation with experimental data. So of course, when you have an engineering application, you must validate your CFD with experimental data, and you have to be careful of the errors coming from the two parts. Okay, as I told you, don't think that the experiments are completely valid because there's a leakage, there's a probe is not calibrated, there's many things, but there's also problems in the CFD. So you have to keep in mind that you must be critical, and this is why you need to be trained in fluid mechanics, in experimental techniques, in processing and all these things. So you can look at the data and say, okay, this is not in agreement because probably this is a problem of my experiment, it was shaking, or I don't know, or it is a problem of my CFD because the boundary condition is too close to the phenomena. So you have to be critical when you do that. But of course you have to validate, and there's many strategies of validation. So there's, let's say, numerical strategies to see that your model is consistent. You change the mesh, you want to see mesh convergence, for example. You want to compare different models. When you increase the accuracy and you see that indeed you have, and then you compare with experiments.
Do you find any limitation with the commercial software? So
of course.
so
yeah, of course.
Tell them.
I told them. I warned them a lot that 99% of the simulation that they can do without any training will be for the trash bin.
Also grid selection, you alluded to something, grid selection, how do we select when to start and then you do independence ready?
Usually this is one of the easy point, because if you have the computer, powerful computer, what you should obtain is, as you mesh finer and finer, at some point the simulation points should not move. Okay, so let's say you have a So let's say you make, so you have a process, I don't know, and you make a velocity profile somewhere, okay? So you have a velocity which is like this, as a function of x, and you plot the velocity of something. Okay, so you do that for delta x equal to 10. And then you make refinement, okay? So you refine the mesh, and you do a simulation with delta x equal to 5. So you will find maybe something, okay, something like this. So still there is some dependence as a function of the mesh grid. So mesh grid or time step also. So now you do delta x equal 1, and then it will be almost fitting. And then you do delta x equal to 0.1, and at some point you expect that you don't see any variation. Okay, so this is what is grid convergence. So you do many simulations by refining the mesh, and at some point the profile should not evolve when you go from one mesh to the next mesh, to the finer mesh. Because you have to keep in mind that the CFD is providing you a discrete solution of continuous equations. So we expect that as the mesh is becoming finer and finer, it should be like a continuous solution. So this is usually what we do. But of course, when you go from there to there, you have divided by 100 the mesh grid in the probably in the three directions. So that is 100 times more time consuming. So usually this convergence, you do that only on one case. You say, okay, I'm going to take these operating conditions, I run simulation with finer grids, I look at convergence, and when I obtain the convergence, let's say 0.1 is converged, so you are happy, but it is very time consuming. So you are not going to look at all the operating conditions you want to simulate with the finer mesh, because that would be huge computation. So you are going to say, okay, 0.1 is converged, but finally delta x equal 2 is not so far. That's enough for me, and I'm saving time, and I'm running all my simulation with delta x over 2, and I know that I have, let's say, 5% error based on that. So this is usually what you do. You go further in grid convergence, and then you go backward to select a mesh which is coarse enough to have acceptable CPU demand. Yep.
How will I identify fine and coarse size particle in a slurry?
Okay, so I'm going to talk about particles. In the next slide, I'm going to talk about particles, the way to handle particles.
Is it based on color difference, I think so?
Is it based on?
Color difference, fine and coarse size particle?
Yeah, of course. You will see that it is based on, with particles there are new problems. Yeah. So you see, so it's now here. So CFD for suspension, and I'm going to illustrate the suspension, CFD for suspension with some applications. Okay, so for each technique, I'm going to show you some pictures, some results that we get, just to show you what are the type of results that you can expect. Okay, so that will be 5 and 6 together. Okay, so when you do CFD of multi-phase flows, you are facing new problems, which are very similar to turbulence. The new problems are coming from the size and the time scales. So you have seen that in turbulence, what is difficult is to simulate the whole domain, the size of the container, and the small scales. And when you have turbulent two-phase flow with suspension, for example, you are facing the same problem, because you will have a process of size 10 meters, but inside you have particles of maybe 1 millimeter. And you know that around that particle of 1 millimeter, it has a wake. It has a wake of maybe 1 or 2 millimeters. So in theory, you should mesh the wake of all the particles. And how many particles do you get in your process? I don't know, 1 million, 1 billion, 1 trillion. So you see that it is completely unfeasible to do direct numerical simulation of particulate flows, because that would need to mesh dimensions which are related to the size of the particles. So let's say you have a process with fines, like, I don't know, 1 micron, 2 microns. Each of these fine particles have a wake of the same size, similar to the radius. And you have trillions of particles, and your process is 10 meters. So you understand that it is completely infeasible. For turbulence, it was infeasible for maybe 10, 20, 50 years. For two-phase flow, that will be infeasible for 50, 100 years. Okay? So we need to do, so you can tell me, okay, I'm not doing any CFD of that stuff. I don't want to do that because it's completely wrong. Okay, so some people are making experiments which are also wrong, but okay. But if you want to do CFD, you have to do something. You have to do some modeling. Okay, so you have to, and then you have to select. You have to select at which scale you want to do the simulation. So what is the length scale you need to get a physical answer that you can use, either for answering to an industrial question, or either to answer to an academic question. And this is typically what we do in CFD of multi-phase flows. So sometimes we do CFD of the complex problem. So this is what you were asking me about fluidized bed. So this is a fluidized bed actually. In this fluidized bed, the typical questions of the people are what is the mean height of the fluidized bed? What is the rate of agitation into the fluidized bed, because it will be related to I don't know, the chemical reaction rate and so on. And for that, you don't need to solve the flow at the scale of each particle. You cannot, but you don't need actually. You don't care if the particles are like this or like this or like this. What you want to see is the large scale of the system. So you are going to plug models to be able to solve new equations, which are not the Navier-Stokes equations, that are able to reproduce the large scale motion of the particles, of the fluid, the interaction, and so on. Sometimes the question might be related to a bit more specific problems, because you have collisions between particles, and you expect that this collision is a very important phenomena. So you cannot do the simulation at that scale because you don't see the particles. So you are going to choose a numerical approach which is able to follow the particles themselves. But of course, instead of simulating billions or trillions of particles, you are going to simulate maybe hundreds or thousands of particles. And then based on that, maybe what you can do is to get statistics at this level to feed some modeling at the largest scales. And then you understand the physics here with a simplified geometry, with less particles, with a simple flow, but you will understand a more specific academic phenomenon. And you use that to feed multi-phase modeling for industrial applications. Okay? And sometimes you need really to know what is exactly the flow around the particles, because you think that really close to the particle everything is happening. So for example, in the wake or in the boundary layer, you need to know what is the rate of transfer of one species, or you need to know what is the rate of collision, or what is the rate of sedimentation. I don't know. You need to know something at the scale of 1 or 2 particles. And then you see that you are going to use all the power of your computer to mesh the flow field around your particle. And to do that simulation, we are using the full power of parallel computing available now. Okay, so you see that to go from here to here with the same mesh, it's completely impossible, because we are able to solve very accurately maybe 3, 4, 5, 10 particles with very fine grid like this. If you go to billions or trillions of particles, it's very, very, very far from being possible. So you need modeling, okay? And I'm going to now to show you different scales of modeling. Okay, so your question would be, what are the assumptions for that? Okay, and the assumptions for that, we will see that there are many. There are many open problems in the modeling, because you have new terms. So I told you with the turbulence you have new unknowns. When you do multi-phase modeling, instead of having 6 new unknowns like in turbulence, you still have that one, because multi-phase flow are turbulent. So you still have the problems of turbulence, but you have also new problems coming from one-way coupling, two-way coupling, three-way coupling, four-way coupling, and you have all these bricks that you need to add to your Navier-Stokes equation. And then as much as you have modeling, as much you have to input physics into your simulation, and as much you may have errors, but as much we get job as researchers and industrials. Okay, if that would be simple, that will be done, and we don't do that, and we are not talking about fluid mechanics, that would be over. Okay, that would be over. But it's not the case. It will be open for many years.
No, actually, another way of reducing is also, if I have a focus objective, like say suppose in my column I am having wear at a particular zone, then I can go for fine meshing at the zone, and then I can look at that what is happening.
Yeah, yeah.
So then the problem is very specific. But if you want to have a generic model, then you have a lot of assumptions.
Exactly. And this is usually when we talk with industrial colleagues, this is usually the first part of the discussion is,
exactly.
Okay, so you have an industrial plant, you have an industrial process, many things are going on inside. Exactly. So you have flows, you have particles, you may have heat and mass transfer, chemical reactions. So you have many things. And you have one problem. I don't know, the thing is clogging somewhere. Exactly. You have a hole because of wearing at some point. The temperature is too high, and then you may blow up your system. So you have one problem. And the question is, among all the different physical, chemical, thermodynamical problems, which one we expect is controlling the answer of your problem? So this is the first discussion that we have with industrial, is to try to go for something which is very complex to one question that we can try to answer. Because if you keep everything together, you are not going to give any answer to nobody. Okay? And for doing that, you need to be trained. So this is why the students are taking courses of fluid mechanics, of thermodynamics, of chemical engineering, of chemistry, of solid mechanics, of applied math a bit. Because you need to be able, when you go and look for a complex industrial problems, and all industrial problems are complex because you do many things together. You need to be able to say, okay, that there are heat and mass transfer, but the problem of clogging is not coming from that. I'm sure it is not coming from that. It is coming because I have particles. Okay. Sometimes it's very obvious. So you can say, for example, if you have a bus, let's say you have a bus, and the bus, you want to reduce the drag because it is consuming too much oil. You are not going to change the size of the wheel. Okay, this is obvious. Okay, but this is because you know that the drag on the bus is related to the shape of the bus and not to the size of the wheel. Okay, but in an industrial process it's the same. It's a bit less obvious, but in an industrial process you have many things, many problems, many chemical problems, fluid mechanics problems. So you need to be able to identify what is the question, and then you can extract the question and try to answer to that question, and then go and feedback with the industrial company and say, I fixed that, try to do that. If you see improvement, it is good. And then we come to another problem. And in two-phase flow, this is the only strategy that you can do. You cannot make the whole simulation of everything all together.
Actually, that is the misconception many people are having. That for a very complex system, I want a complete modeling of the system. That CFD cannot deliver that.
No.
At least with the, say, the computational power what we have, because then the computational power has to go up by 10 to the power 6.
Exactly.
Then only it is possible. So actually that is why I raised this question.
Yeah, sure.
Many people, they have this
So
wrong notion. Okay, I want to model this separator by CFD. I always say that you cannot do that. You specify that what is that aspect.
Exactly. So and this is the work of, and this is why you have, let's say, from academic to production, you have many steps. So you have the people in charge of production, so they are facing the real problem, and they have to explain to people in the company which are a bit more specialists of science. So they are going to separate the different things, and then they are going to discuss with academics which are able to talk to industrial people because they understand the question, and then they can go back to really fundamental people that are just looking at equations but they don't know what these equations are meaning, and then they are going to talk to people who are just coding and they don't know exactly what will be the answer at the end. Okay, so this is why we need many steps, and we need many type of scientists in between, and all of them have a role, and if you have somewhere a wrong connection, then you lose the interest.
And then for that purpose, many times you have to collaborate with others also.
Exactly. And this is why the students are trained to many disciplines, because you may think that when you do mineral processing or when you do chemical engineering, you don't care about the mathematics, but actually you see that all the equations.
That's why I'm saying that CFD is not like a video game. And you will just get a solution immediately, and this is the wrong notion many people have.
No, it's very. You may have something. You will have pictures. You will have movies, but very often that might be wrong, and you don't know how to analyze that. Okay, so you have to be trained in many, and it is quite long to really understand what is the response of your CFD code, where the problem is coming from, and so on. So. But it's what is interesting. So this is why you have professors, you have industrial, and this is what we are keeping working on that topic. It's because it's completely open. There's many questions, many issues, many things to do. So I'm going to give you some examples of the different scales. So this is, for example, the type of diagram. So I told you when you have a code, you have to select options. So this is typically the type of questions that you have to ask you when you do CFD. So you see when you do CFD of single phase flow, you have maybe 3-4 questions that you have to answer. When you do CFD of multi-phase flow, you will have much more questions to answer when you want to select a model. So I'm not going to explain everything, just to show you that this is complex. And anytime you make a choice, anytime you give the wrong answer, okay? Most of the time you give the wrong answer. But not only you, myself as well. You know, when I do simulations, very often I'm starting with something that I know it is wrong, but it is quick. So I get the answer quickly. I know it is wrong, but I will try to understand why it is wrong and what I have to fix. Okay, so even the professors are making errors, and we are making a lot, of course. But because we made many errors, so we can teach you.
What is the benefit of getting wrong answers quickly?
It at least to start to identify where are the open issues. So, for example, if you identify that when you do this simulation, then this is this part of the system where the code is blowing up, it means that you need to understand what is going on there. And it's also because let's say if you make a choice which is very CPU demanding. So you make a choice, you think it is maybe the good choice, but you will get the answer in 1 month. And finally, it's not the good answer that you are expecting, so you are going to wait again 1 month to make another test. So usually, when we do this CFD, we start by rough models, rough assumptions, we see, and then we refine up to what we expect to be the best answer. So you have to go step by step. But when you get the first answer, you don't have to believe that this is the correct one. Okay, so these are all the different models that you can find in the literature. Okay, so this is a way to classify the two-phase flow approaches for simulation, for form. And it is all based, you see, on the ratio between the size of the particle and the Kolmogorov scale. So remember, in a turbulent flow, you have the smallest eddies, and the question is, your particles, is it smaller or larger than these smaller eddies? Very often you have to decide which model you are going to use depending on this criterion. How big are your particles compared to the flow structures? Okay? And you see that if you go from so these are the very fine particles, and these are the very coarse particles. So that was the question you were raising. So you see that numerical techniques are different if you are using very small particles, intermediate particles, or big particles. And what I mean by small or big is not the size, is not 10 microns, 50 microns, 1 millimeter, 1 centimeter, is the ratio of the size with the turbulent scales. This is what is important. The real size, we don't care. It's really, do we need to mesh the flow around the particles because we have flow structure at this scale, or we don't need. Okay?
But the density of particle you don't consider.
No, it's not very important. Of course, if you have gravity, then you have settling, you will have new features, but it's not, gravity has no effect on the selection of the model, the type of model. It will have an effect on the physics, on the results, but not on the type of model. So let's say that you have very, very, very fine particles. So this is what we call a dusty gas or a dusty liquid. So you have, it's like if you have a liquid with only fines, and the geometry is very broad. So in that case, you can assume that the particles are all in suspended by the flow, and they are flowing with the flow without any slip. Okay, they are just following the flow. The only thing that is changed is the density of the equivalent medium and maybe the viscosity. As we saw yesterday, you will change the viscosity depending on the concentration of that fine particles. So that will change the Reynolds number, that will change the behavior of the flow, but finally you assume that it is almost like a single phase flow. You don't care about the particles, it's just modification of the physical properties. The problem for that in your, let's say, in the course mindset is that this approach is not appropriate for separation processes because we assume that the particles are following the fluid. So if you want to separate the particles from the fluid, of course this technique is not adapted, is not suitable. Okay? So this technique is useful for other applications, but not for what you are training to in that courses, which are separation techniques. Okay? Because in that assumption, particles and fluid are completely attached, but you cannot separate them. Okay, so I'm not going to talk about that because it's meaningless for you. So now we extend a bit the size of the particle, and now we are going to have equations which are different for the particles and for the fluid in order to be able to have slip and then maybe to do separation. So I can give you some examples of what we did. So for example, we were at some point facing a problem with Total on hydrocyclones. So this is where I'm starting to collaborate with Professor Majumdar. And we want to know what is the dynamics of the particles and of the fluid flow into this part of the process. So again, you say, I'm not going to simulate the whole thing. I'm going to focus on one aspect of the process. And some people are working on the whole thing. With the people doing engineering, process engineering, they are going to look at all these operations as black box with flow rate, input, output, and we are going to optimize the whole process. But I'm going to look at only one specific part of the process. Okay, so you probably know what is a hydrocyclone. So you have fluid coming in, it will swirl, and because of the swirl, you remember when you have rotation, particles which are denser than the fluid, they will be centrifuged, and because they are centrifuged, they will be collected by the walls, and then they slide and go back and go down to the underflow, and the fluid, the pure fluid we expect, is going up, and then we separate the solid from the fluid. Okay. You can find empirical models, and then we decided to do CFD to understand a bit with more deep knowledge what is going on in the hydrocyclone. So we did the CFD. You have a choice, again, as I told you. So we have the choice between K epsilon, RSM, all these models. So we did it progressively. So we did first simulation with the simple one to see if we can get the flow structure quite, let's say, coarse, to have the general structure of the flow. And based on that, you can also go from one model to another model by refining the accuracy of the model. And then you don't start from scratch. So you start from the previous answer to refine it with a better model. So you save CPU instead of starting from scratch. And we have some experiments that we can compare with, trying to validate the model. And that configuration is actually quite complex. You could think it is simple actually, but the geometry is not very simple. You see, you have tangential inlet, you have cylindrical part, conical part, you have particles, turbulence, you have a wall, you have also some gas in between. So it's actually a very complex system. Okay, so what we did is to use this set of equations. Okay, so just to show you. So you see that the equations are very, in terms of structures, they are similar to the Navier-Stokes equations, because you see you have here mass balance equation, so divergence of something, temporal variation of something. Here you have momentum balance. You have exchange of momentum between the phases. But inside all these terms, you need to use modeling. Okay, so you need to select a model for your flow. You need to use a model for the particles, because we are not going to solve the motion of each particle. We are going to solve an equation for the concentration of the particle or for the agitation of the particle. Okay, so we are not going to use the force balance I taught you. Okay, so we are going to use average equations, and each time you do averages, you lose some information, and you have to plug models inside. So we have many choices to evaluate the viscosity of the system, the viscosity of the suspension. So we had many things, and this is why you need to have expertise to select the appropriate models to get the best answer you can get. So here, in terms of equation, you have one equation of mass balance and three equations for the momentum for the fluid. And then in the real system, you have different sizes of particles. So we are going to solve the equations, but for different sizes. So I have a picture of that. So yes. So let's say that this is the PSD particle size distribution of your particles as a function of the diameter. If you want to solve this thing by CFD, you are not going to solve all the different classes, because for each classes we have one mass balance, three equations for momentum. So if we have hundreds of classes, that will be multiplied by 4. That will mean you have 600 equations to solve together over the fine mesh with the complex geometry, and so it's huge. So we decided to discretize also the PSD with different classes, and then you have also the choice here. So if you do a wrong choice on how you evaluate the classes, then of course your simulation will be wrong. And then I go back to the equations. Okay, so you have for each class K from 2 to n, for each class you have a set of equations with mass balance, momentum balance, and you solve everything. And at some point you get so this is the mesh that we used. And then at some point we did the validation as you proposed. So we did the validation first for water only, because it is easier. You don't have the particles, even in terms of experiments, it's easier without the particles. So we did simulation, and then you see, for example, that if you use one model, K epsilon, which is the less accurate and the less demanding in terms of resource, you see that the red line are very far from the dot, which are the experiments. Okay, so the black dots are the measurements, and you see that the red points, which have been obtained with one model, is not accurate at all. And then if we move to another model, RAG, RSM, then we get a better agreement with the experiment. It's not perfect, but it's much better. And it is because the K epsilon, there is one assumption that the turbulence is isotropic, but in that flow, it is very anisotropic, because you have this big swirl. Okay, so of course, I was expecting that the turbulence is not isotropic, but I decided to use K epsilon as a first guess. And then when you refine, of course, when you go from K epsilon to RAG epsilon, the time of the simulation is multiplied by 10. Okay, so you have a better answer, but you lose time. Okay, but still we had the first guess with that flow, which is not correct, but you can use that as the first estimate to run a better simulation. And then we looked at the particle size separation, and then again we compare with the experiments. So you see the experiments are the dot, black dot, and the simulations are the stars and the plus, and we get a good agreement. And actually we get a better agreement than what is used for the design, which are the correlations, complete correlation, which is very often used for doing that. So you see that if you do a good job in CFD, you can get very accurate results. But if I show you the results that you can get with this wrong model, that will be completely wrong. Okay? And if you don't have any idea of the results, if you don't have any validation, experimental validation, you may think that this is a correct answer, and it's completely wrong. Okay? So you see that the results are drastically depending on the model you choose. Okay, so you have to make a break to switch the memory card. So maybe the kind of validation you can do. So you are going to compare with some efficiency, separation efficiency of your system, and then the nice thing is now if it is validated and you can trust, so you can see inside what will be the concentration, the local concentration of the particles. This is something that you are completely unable to measure. Whatever the technique you want to use, it's completely impossible. So you can have access to new information, and based on this new information, you can have ideas for optimizing or designing a new process. Okay, so this is really a tool to understand. Okay, so these are the experiments we did to validate. Okay, so I skip that. Okay, so now I'm going up in terms of size. So now the particles, I think that I need to solve the motion of all the particles, because I think the physics is there. I need to know where the particles are moving, what are the collisions between the particles, because I think the answer is there. Okay, so I cannot avoid the simulation of that particle, and this is what we did with the momentum balance, the force balance that we saw yesterday. Okay, so let's again show you an example of something that we did. So we did simulation within a Taylor-Couette device, so it's actually very simple in terms of geometry. So you have a cylinder which is rotating, the outer cylinder is fixed, and then you have a fluid in the gap between the two cylinders. We are solving the Navier-Stokes equation with the appropriate Reynolds number, which is based on the rotation of the cylinder and on the gap and the viscosity of the liquid. And then inside that we want to insert particles, because we want to know how they are going to be separated by this system, because again you have rotation, so we expect that dense particles are going to be centrifuged and light particles should be collected on the inner wall, okay, on the inner cylinder. So we want to do this type of simulation first with one-way coupling, just to look at the dispersion, where the particles are going. And as I said, we will then you move to another method which is better, which is two-way coupling, because we expect that the particles are going to modify also the motion of the fluid. So we do first some simulation which are quite simple, and then we enrich the content of the simulation by using two-way coupling. Okay. So the flow, actually the geometry is simple, but the flow is quite complex. So you go from the pure quad flow that you may have solved analytically to a first instability where you see vortices. These vortices, they are like, it's like a tire, like a toroidal vortex. These vortex are going to oscillate and they have to be modulated, and finally you have turbulence. So the flow is evolving toward turbulence very progressively. So we did simulation of this to be sure that we get the good thresholds between all the instabilities, and finally we did the simulation of the turbulent vortices when we were able to solve the flow at the different steps. So we validate it. So this is the type of flow that you get. Okay, so this is a turbulent flow, and you see close to the inner wall and the outer wall, you see the turbulence. So it may be better on that screen. You see the turbulent structures, and they are fully resolved. Okay, so it's pure DNS, no modeling. So we can have confidence, and then we compare that with the torque that you need to exert on the cylinder to keep the rotation of the fluid, because you have dissipation, so you need to inject power into the system. So we compare with experiments, so the lines are correlations based on experiments, and then we compare our simulations, and it seems to work. Okay, so this is the type of information that you can get. Okay, so in terms of flow, so you see we have access to all the flow structures. So you see the vortices, these are snapshot of planes, vertical planes, and you see everything. You see the vortices, you see the intensity of the vortices, and this is evolving along the azimuthal direction, and this is evolving in time. So it's like if you have a very nice experiment where you can measure everything. You can measure the velocity in the free components. You can measure that at any point, at any time. So it's very the ideal experiment, because you have access to anything when you are sure that this is the correct answer. And in that case, we are solving the Navier-Stokes equation with a very precise, accurate code. But it is very time consuming. You see, about 5 million points. And the Renners number is not very high. It's probably, yeah, it's 5,000, not very high actually. Okay, so we look at the flow structure, and then we were interested in the tracking of particles. Okay, so now we have this flow, and on that flow we want to solve the Lagrangian tracking. So you remember that in the Lagrangian tracking you need to use the flow information. You need to use u, the velocity, and the gradient of u. But your particles are not going to follow the mesh. Okay, they are not. The trajectory is not like if your mesh is like this. If your mesh is like this, the particle is not moving like that. Okay, the particle is going to move across the domain, but is not going to fit the corners of your mesh. So you need to do interpolation. For example, when the particle is here, you know the velocity only here, 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 and here. So you need to do interpolation to get the information of the fluid velocity and the fluid gradient at the position of the particle. Okay, so there is a new step in terms of modeling. This is how do you make the interpolation, and you have the choice. There are many schemes of interpolation. Okay, and based on that, you can solve the force balance, and then you can have the trajectories of the particle. And at some point, what we want to do is to have the feedback effect of the particles on the fluid elements. And this is something that I've shown you. So we solve, so you know this equation with all the good modeling, but even there are some assumptions. You remember, it has to be spherical, it has to be small, it has to be rigid. So there are some assumptions. If your experiments are with not spherical but with oblate particles, then you don't know how to do that. Okay, there are some assumptions, and then we look at the dispersion. So we inject particles and we look into the flow, how they are going to disperse, and we have identified that within that turbulent flow, actually there is a strong accumulation of that particles very close to the wall into some turbulent structures that you cannot resolve with Reynolds average Navier-Stokes equation because you lose all this information. So based on that, we were able to investigate some new phenomena which are related to turbulent flow and preferential accumulation of particles close to the walls. And then, because you have here accumulation, we expect that you will get modification of the flow due to this accumulation. So we compare with some experiments that the accumulation is what you observe in experiments. And at some point we use the feedback effect. So instead of the Navier-Stokes equation, now we are going to solve the modified Navier-Stokes equation by the presence of the particles. So we have new terms everywhere in red, you see, involving the concentration, the local concentration of particles, and the feedback effect due to momentum transfer. And that will be modified the flow. So for example, we looked at the torque acting on the cylinder, comparing single phase with two-phase flow. And indeed, we see that as time goes on, there is a modification of the torque. So you may have an increase of the torque or a decrease of the torque due to the presence of particles inside the system. Okay? And for doing that, if you do the same with Reynolds average Navier-Stokes equation, you will lose completely the information because you don't have all these fine structures where the particles are collecting. Okay, so we compare, and you can show that if you don't take this care, the care to track, to resolve these flow structures, then you are missing the physics. You are completely missing the physics. Okay. So this is what you can do when you are at this scale. So you see Lagrangian point tracking, and to conclude, sometimes you need to resolve really the real size of the particle, because in that simulation, here we are assuming that the particles are points, okay, because the particle is moving through the mesh, but the particle is smaller than the mesh grid. So I don't have any idea about the flow around the particle, if there is collision, I don't know anything about that. That was enough to understand that physics, but maybe in some cases you need to do the full resolution, fully resolved particles. So I mean, you have a particle like this, and you want to know exactly what is the flow around that particle and how it will interact with other particles. So like what we saw, when a particle is going to collide with a wall, because of the fluid which is around, it has to drain, then the coefficient of rebound is different. In that case, if you are not solving the motion of the flow around the particle, you are going to lose that physics. Okay, so sometimes you need, for specific problems, you need to, so I'm not going to talk about the technique, I'm going to show you some examples. So for example here, when you have two particles in line in a Poiseuille flow, the first particle is not experiencing the same force as the second one. So if you assume that they are just point particles, you lose this information because you assume that the drag will be the same for the first and the second particle. But in reality, it's different. And in some cases, that is very important, and especially for migration problems. So we did many validations. And here we use that technique. So this is the kind of information that you can get here. So you see all the black dot or the white dot are actually particles which has been fully meshed. So the mesh is, let's say, 10 or 20 times smaller than the diameter of the particle. And then we have the full access of the fluid. You see the fluid. Actually, these arrows, I just took 1/10 because you cannot see it, there's too much. But we have the full access to the fluid in between all the particles here. And then from that, we can, for example, evaluate the rate of settling. We can evaluate what are the fluctuations of the settling velocity. We can evaluate many things because, let's say you have a gravity settler, you have many particles, and then we took a cube, like 1 millimeter, where we have maybe 100 particles. And on that cube, very small cube, then we have all the hydrodynamic interaction, and then we can extract some statistics and compare that statistics to the full tank, and maybe it's good. But you don't have the effect of the wall. So maybe you have big recirculation into the system that I don't have in that simulation. So this is why you need to do what we call multi-scale analysis. You need to know the physics at the microscopic scale, but you need also to handle the whole domain, because you may have structures of the flow which are very big. Okay? So we look at different phenomena. So you will have the slides. So I gave the slide on the computer. You can have a look at the slides. There are some references. We did also simulations with turbulent flow. So here we are doing direct numerical simulation of a turbulent flow. So you see all the flow structure. So I told you you remember the vortices and the spaghettis. So this is what you get in a DNS of turbulent flow. And then we placed particles into that flow. So each particle is resolved by 10 grid points. And then we have full access to what is the effect of particles on turbulence. So I told you that there is an open question: does it enhance or does it damp the turbulence? And with that types of simulation in a very academic system, because it's only a cube of fluid with no walls, nothing, then you can see what will be the effect of particles, for example, on the agitation of the fluid. So you can do the same simulation with single phase, with particles, different densities, different sizes, and then you compare what will be the response of the flow due to that particles. And the idea is when you do that on a very small cube, you are going to make statistics on that cube, and that will be a model so to what is happening in the process if you look locally at one point. So you can use the statistics that you form with that type of simulation to feed modeling at a very large scale, because we need everywhere. You remember you have U prime V prime bar. So now I'm able to predict what will be U prime V prime bar for this suspension. And then I can feed a simulation with a large scale, with a K epsilon model. But now I have fixed one of the key points of the modeling. Okay, so we looked at statistics and very complex things. Okay, and finally, so I told you in the introduction that we don't know how the particles are modifying the threshold of instability and the threshold of turbulence onset in a pipe. So we decided to use this type of method because we know that we are solving everything the best as we can do. And then we try to do simulation of one point, because it is very time consuming, so I cannot do all the points of the experiments because of limitation of time. And for that, so here, this is what I was telling you. So this is the flow structures close to the wall. Actually, the turbulence is coming from the wall, and then it will, all these vortices are lift up and go back and go into the bulk where you have the turbulence. But all the turbulence is controlled at the wall. So we feed the turbulence with particles. So I don't remember, so 3,000 particles. So now we are able to do 10,000 because it was 1 year ago. So the computer is now more powerful. And then we look at we compare, for example, what is the flow structure single phase. So these are snapshots of the flow at different planes, different height, single phase, with the simulation with particles. And with particles, you see that the flow is drastically different. You see that all these big structures, blue and red, are broken by the presence of the particles. And we propose a physical mechanism to explain why it has modified the onset of turbulence, because it has modified what is called the regeneration cycle of turbulence, a kind of mechanism to generate turbulence. And with the presence of particles, that will modify this instability. So with that kind of simulation, we have access to the full information around the particle. But again, that will be completely unfeasible to use that for a process, because you need too much time. But you can use that to understand the physics, to take statistics, and then to feed modeling more accurately, more physically, to get a better answer for applications to the industry. Okay, I have many statistics, many papers, and then I'm stopping here. Okay, so thank you for your attention.
There will be